Hey, my name's Patterson, and today we're going to be talking about image formation by lenses. So, as you probably know, lenses are used in a lot of everyday things, including glasses, cameras, projectors, and many other items. But before we get too deep into the topic, there are a few definitions that we should know. The first definition is the focal point, which is characterized by the capital letter F, and that's simply where light beams cross each other. The second, but lowercase f, is called the focal length, which is the distance from the center of the lens to its focal point. And that can be either on the left or the right side of the lens, depending on where the light is coming from. And then the power of the lens is the inverse of its focal length, and it's found just using the equation P equals 1 over f, or the focal length. And one thing to note is that the units for power are not in watts, but are in diopters, and the unit for that is just a capital D. Now, the first type of lens we'll talk about is a converging or a convex lens. And this is a lens where light rays that enter it parallel to its axis, they cross each other at a single point on the opposite side with a converging effect. And the next few pictures will illustrate the idea of what I'm talking about. So here, the rays that enter into this lens, they exit at a different angle because of the refraction that is happening inside the lens, and that's because the index of refraction of the lens is greater than that of the air, and this is according to Snell's law of refraction. In this picture, the same idea is shown, just with all three of the rays that enter into this lens. And you can see the capital F, which is the focal point of the lens, and the lowercase f, which is the focal length of the lens. And because of the lens's shape, the light is bent towards the axis at both surfaces. The next type of lens we're talking about is a concave lens, which is a type of diverging lens. And this is a lens which causes the light rays that enter it to diverge from the axis, or to spread out. So that's why it's called a diverging lens. The difference between this and a converging lens is that a diverging lens's focal length and power are negative. And the reason why they're negative is because the focal point is on the left side of this lens, and by definition, anytime the focal point is on the left of the lens, it's a negative value. And that causes the focal length to be a negative value, and such, when you plug it into the power equation, you're going to get a negative value overall. The next lens is called a thin lens, and this is described as one whose thickness allows rays to refract, but it doesn't allow dispersion and aberrations. So an ideal lens would have two refracting surfaces, but the lens would be thin enough to assume that the light rays bend only once. And a symmetrical lens also has two focal points, one on both sides of the lens, and they're both equidistant. And the light rays that pass through a thin lens's center are deflected by a minimal amount. So a technique that people use to follow the paths that light rays take is through a process called ray tracing. And there are 5 rules for ray tracing, and we'll go over each. So rule number 1 is that a ray that enters a converging lens parallel to its axis passes through the focal point of the lens on the other side. So as you can see, this woman is standing here, and the ray is moving parallel to the lens, and then once it enters the lens, it is refracted and it is bent so that it enters the focal point on the other side of the lens. Rule number 2 is that a ray that enters a diverging lens parallel to its axis seems to come from the focal point F. So as you can see, the focal point is on the left, and the ray is coming from the left parallel to the focal point. But once it enters the lens, it is refracted off. And to us, it looks like that because of that refraction of that ray, it looks like the ray is actually coming from the focal point itself. Rule number 3 is that a ray that passes through the center of either a converging or a diverging lens, concave or convex lens, it doesn't change direction. So you can see that this person has a ray of light coming from them, but once it enters the center of the lens, it keeps going at the same angle. Rule 4 is that a ray that enters a converging lens through its focal point exits parallel to its axis. So here in this illustration, you can see this ray coming in and it's hitting the focal point to the left of the lens, and once it enters the lens, it is refracted and causes it to leave parallel to the axis. The fifth rule states that a ray that enters a diverging lens by heading towards the focal point on the opposite side exits parallel to the axis. So we see this ray that is entering this concave lens, and it should keep going straight and enter the rear focal point over here on the right. But because of this lens, it is refracted and actually exits parallel to the axis. So there are two types of images we'll go over. The first one is called a real image. A real image is an image where the light rays from one point on the object cross at the location of the image and can be projected onto things such as a screen or even a piece of paper. So as we can see from this diagram, we have two rays of light leaving the object and passing through the lens. The top ray follows the first rule of ray tracing, where a ray passing parallel to the axis will change direction and pass through the focal points of the lens on the other side. The second ray follows the third rule of ray tracing and continues to move in a diagonal fashion towards the center of the lens to help create an inverse image. This picture gives more of an idea of what I'm talking about, and an important thing to note is that when remembering the difference between real and virtual images, you have to remember that the light rays from the object will actually come back together in a real image, which is why you can project things onto a surface. So this picture just reiterates the past few points I've made, and basically the lamp is being shown through a convex lens and is projected onto this piece of paper inversely, and that is a characteristic of a real image, is an inverse image or a flipped image being projected. The next type of image is a virtual image. So a virtual image is an image that's on the same side of the lens as the object and cannot be projected. So from this diagram, we have two light rays. The top ray is following the second rule of ray tracing, where a ray that enters parallel to the lens will diverge as it enters the lens and leave. However, the dashed lines show how the ray seems to originate from a focal point in front of the lens. And this is important as we continue on with our discussion of a virtual lens. So the next ray continues through the center of the lens in a diagonal direction and leaves. But we have to note that none of the light rays ever cross each other. But our eyes interpret the rays to be crossing each other in front of the lens, which is why we can see a virtual image, but we cannot project it. This image also appears smaller than the actual object itself. So a real-life application of a virtual image can be seen through this example. So I have a glasses case down below, and also I have a pair of my glasses. So I'm a nearsighted person, which means I have to use a pair of concave lenses or a diverging lens to correct my vision. And as such, it makes a virtual image appear smaller than what the actual object itself is showing. So let me just show you what I mean. So as I hold my lens up to the camera, you can see the object here. When I take it off, the object appears to increase in size. Put it on, take it off, on, off. And this is because a focal point is being created that is smaller, that creates an image which appears smaller than the actual object itself.